Hello everyone, I'm Nikhil. I'm a postdoc in the project Urban Stream Corridors and I am handling hydroclimatology part of the project. So today I will be sharing our methodologies and findings on compound precipitation wind extremes in the Bay Area. So what exactly is a compound precipitation wind extreme event? So if you can see the figure, the on the x-axis of the figure, there are wind speed variable and the precipitation variable. On the y-axis, we have time. So day one, day two, day three, and all the way up to day 365. So these red dotted lines, these are the 98th percentile threshold for wind speed and for precipitation. And these stars, these are the different values of the precipitation and wind speed on these days. So, according to our definition, which is a compound event occurs when both precipitation and wind exceed the 98th percentile at individual grid points. So, in this case, day one, where the 98th percentile for both precipitation and wind speed is exceeded, is registered as a compound event. So, this methodology is called a peak over threshold method, which is used to separate these daily bivariate events. So, now that we have identified what a CPWE is, you might be curious about how often these events can occur. How do we calculate their frequency? Like in our study, we firstly determine this through the return period. So, how the return period has calculated? So, if you can just see the figure, it is the same figure from the previous slide. So, in this case, we have one event. Let's say if we have one event, one compound event in the whole 365 days. So, so we calculate the return period. It is the inverse of the probability of an event. That is, if we have to calculate the return period in years, that is number of years in the study period divided by total number of events. So total number of events in this case is one, and the number of years in the study period is also one. So that means that the return period is 1 year. That is, such event is happening like every year for this particular data. So like further moving on. So this is the methodology of compound precipitation wind extremes, the whole framework. So here I will be focusing on this observed data and the return period analysis first. So, what for the past, we compiled grid met data and obtained extreme events through the 98th percentile of daily precipitation and daily wind speed. After getting the compound precipitation wind extremes, we calculated the return period analysis for the whole of the Bay Area. So let's delve into the results of a crucial piece of our methodology, that is 98 percentiles and the return period analysis. So so there is a very important point, like, which is noteworthy, that we have taken into consideration the wet season from October till April. So this is because post summer, by September, the soil typically exhibit significant dryness due to prolonged dry periods. Therefore, the starting month is selected as October. And like in the wet conditions in the April, that is, sustained moisture is present, like after rainy season, and so any precipitation event can initiate flash flooding. So therefore, the ending month is October. So this map illustrates the 98 percentiles of precipitation, and this represents the 98th percentile of the wind speed. So the first map represents the like 98th percentile at an annual scale, the second one at the on the wet season, and the third one on the dry season. Similarly for the wind speeds as well. And this is the legend for both of the 98th percentile for precipitation and wind speeds. So in terms of precipitation, we can see that the 98th percentile are relatively higher in the wet season than annually, like as it is expected, because the 98th percentiles in the wet season would be higher because it's the wet season. And but in terms of wind, the wind percentile values are slightly higher in the wet season compared to the dry season, but the difference is very subtle. So now turning on to the return period analysis. So we have analyzed it for both for annual scale and also for the wet season. So what this plot tells us is that uh, this is the return period on the basis of 98th percentile of precipitation and wind extreme events. And this is for the annual season, this is for the wet season. So during the period of 1982 to 2022. So the results that we got from here was for the annual scale, the spatial mean over the Bay Area was about 0.52 years. And if we see the coastal areas, like these coastal areas, except for the Marine County, the the data shows that the return period is about zero point 0.5 to 1 years. And if we move down to the wet season, the spatial mean over Bay Area is about 0.83 years. And majority of the Bay Area, it ranges from zero point 0.5 to 1, that is this blue color. So except this coastal part of the Marine County. So now that I have discussed the return period analysis and the percentiles, let's now focus on the decadal moving average analysis and for the past period. So we have conducted this analysis using mean and trend analysis using man-Kendall test and sense slope, and we have calculated the frequency, and we have calculated the climate during these events, like the precipitation, wind speed, and temperature. So how we have like collected our data? So what we did, if you see the figure, so this is the similar figure that I showed in the previous slides, just extended up to the maximum temperature and minimum temperature. So these are the values for day 1, day 2, and all the way to day 365. So as we can see here that for these are the thresholds for precipitation, these are the threshold for the wind, and there are two compound events which are registered. So what we do is we take these compound events and we make a table sort of like this, and which registers the compound event ID, the date, precipitation, wind speed, maximum temperature, and minimum temperature. So once we have this data set for all the grid points, then we generated the 10-year moving average time series for this precipitation, wind speed, maximum temperature, and minimum temperature. And also, we generated a 10-year moving aggregate time series for the frequency. And after doing that, we conducted a mean and trend analysis using Man-Kendall test and sense loop. So now moving on to how we have conducted this trend analysis. So the trend analysis, it consists of mainly two steps. One first step is the Man-Kendall test, which is a non-parametric test to determine if there is a statistically significant trend in the variable using statistics based on pairwise comparisons. And the second step is the sense slope estimator, which is used to quantify the trend, like to estimate the rate of change using slopes between all pairs of data points. So, median slope is called sense slope. So, what flowchart we have followed in this study is we've done the man candle test and we have followed this table, the z value of 1.96. So if the value z value of 1 is greater than 1.96, that means it is showing an increasing trend and it is statistically significant. And if there is the value is from minus 1.96 to 1.96, that means the our trend is not statistically significant. And if my value is less than minus 1.96, then it means that it has a decreasing trend, and but a statistically significantly decreasing trend. So this is for the 95th percent confidence level. So in this example, if you can see, this is our time series of annual precipitation, and in the graph we can see there is a increasing trend. So if we apply these tests for this time series, we should get values which satisfy the criteria for the increasing trend. So the values that we get is we get the Z statistics of 3.04. That means it has statistically increasing trend. And we get the sense slope of 18.57 mm per year. That means that the rate of increase of annual precipitation is this 18.57, which is increasing. So that's why like in studies we use this trend analysis to detect trends and to quantify trends. Moving on, we have conducted this trend analysis for frequency of CPWE events. So, what this figure tells us, this is the mean frequency of CPW events of a 10-year moving aggregate, and this is the sense slope of the 10-year moving aggregate series. So, we have shown only the significant trends here, which have this like confidence interval of 95%, and it is for the wet season and during the period of 1982 to 2022. So the results of the mean analysis, mean 10-year moving aggregate, shows that there are about 14 events per decade, which is the spatial mean over the Bay Area. And the sense slope also, it has very interesting results that we found that these events have increased in the recent decades for a large segment of the Bay Area. So now we also conducted the analysis for precipitation and wind magnitude during these events. So we calculated the 10-year moving average time series and then their means and the sense slope. So the figure on the first row, this is for the precipitation, and the second row is for the wind. And the first figure is for the mean precipitation during these events, and the second one shows that how this precipitation has been increasing during the past decades. So what we got is that the results for the precipitation were quite interesting. The precipitation during these compound events, they show a significant increase of 0 to 0.5 mm per year, that is this green color, in major segment of Bay Area. Like on the contrary, for the wind speed, wind in these events show a significant decrease in major segment of Bay Area, but the magnitudes are very small. So moving on further, we also calculated the temperature magnitude during these events, and so this figure shows here the 10-year moving average of maximum and minimum temperature during these events for the wet season during 1982 to 2022. So the first row shows the mean maximum temperature and the mean minimum temperature, and the second row shows the sense slope. So what we found was that the temperature trends were not that significant, but the major finding was that during these events, the maximum temperature over the Bay Area was approximately 13.5 degrees Celsius, and the minimum temperature was 7.9 degrees Celsius. So now moving on to the overall like conclusions of these results. So first is The mean return period for these events in the Bay Area is about 0.83 years, which indicates an occurrence nearly once a year. And the second part is for a large segment of Bay Area, these events have increased, like with a rate of more than two events per decade in the recent past. And precipitation during these events in the Bay Area is increasing substantially with the rate of 0 to 5 per decade across most of the region. And during these events, the maximum average and minimum temperature across the Bay Area are 13.5 degrees Celsius and 7.9 degrees Celsius, respectively. So, moving on to the future analysis. So, future analysis is conducted using future climate scenarios, that is, RCPs and SSPs. So, first, the global climate models. So, what are these global climate models? These are complex numerical models which are designed to simulate the Earth's climate system. So what these GCMs do, these GCMs use the different climate scenarios as their input, and they simulate possible future climate conditions. So there are two types of climate scenarios. First is representative concentration pathways, which are based on greenhouse gas trajectories, and the which are used in the IPCC AR5 report. And the second one is the shared socioeconomic pathways, which are also called SSPs, that are described by socioeconomic factors describing emissions. So these are used in the latest IPCC report AR6. If you see this figure, on the y-axis, it is the CO2 equivalent, and on the x-axis, it is the years. So it shows the projected CO2 concentration under different RCP scenarios, and the RCP scenarios and the socioeconomic scenarios, they can be equivalent. So RCP 4.5 is equivalent to SSP 245, and RCP 8.5 is equivalent to SSP 585. So because like they have similar characteristics. So RCP 4.5 and SSP 4.5 are intermediate stabilization scenarios. They are like middle of the road development scenarios. And RCP 8.5 and SSP 5 8. It is a high emission scenario, and which assumes fossil fuel development and high inequality and limited mitigation efforts. So, further, in this study, we will be using this future climate data, that is CMIP 6 based multimodal hydroclimate projection over the contiminous US. So, this data set has seven GCMs. This has four different scenarios, and it has a good spatial resolution of 4 kilometers, which matches our GridMet dataset resolution, and it is available at a daily scale. So, and for the scenarios, we will be using SSP 4.5 and SSP 5 8.5. It is proposed because the California's fourth climate change assessment report, it also utilized RCP 4.5 and RCP 8.5 scenarios in its studies. And if there are any suggestions and alternatives on this, uh, will really appreciate that. So in the end, this is the whole framework that we are going to do. That has already been done for the past, and will be uh, repeated for the future. That is to carry out the return period and decadal analysis for the future period under SSP 245 and SSP 585 scenarios, and also further evaluate future changes in the return period and decadal analysis with the base period as 1982 to 2022. But interestingly, we are also adding one more component here, that is the risk assessment using GIS based socioeconomic data sets for our contemporary analysis. So, this is our another objective here to achieve that. And So to incorporate GIS based socioeconomic data sets to integrate into our risk assessment for the past. So thanks for watching the video, and I hope you have a nice time.